Hi guys, Buildzoid here, and today we're going to be doing a PCB breakdown of this right here. This is an RTX 3060 Ti FTW3 Ultra from EVGA. And before we get into the video, the PCB pictures are from Tech Power Up's review of the card. So big thank you to Tech Power Up for providing high-res PCB pictures. And also, if you'd like to know more details about this card, like thermals, power consumption, performance, you should go check out their review. There will be a link to it down in the description. Now, you might be sitting there wondering, why are we taking a look at a 3060 Ti? Well, basically, I've been kind of considering that, I've started playing games that, actually require graphics these days, because most of what I play is really old, or Minecraft. And so, I've recently been thinking, you know what, it would be nice to have a card that actually sort of keeps up with the games I play that isn't an, because the card that's in my daily system is an RX 580. And it's not doing so great anymore. So, I've been kind of thinking yeah, I'd like an upgrade, and I kind of like the 3060 Ti, because I don't need a crazy fast GPU. I just need something that's faster than a than an RX 580, and at this point, that's not very much of a high bar to reach. And so I looked around at 3060s for a little while, and I came to the conclusion that I like this PCB best for modding. It's not the best 3060 Ti PCB. That wasn't really my criteria. My criteria was which one has the most easily worked with voltage controllers, and that's this one. So, yeah, but before we get into that, and also which one just sort of looks the most moddable, and ultimately that I came to the conclusion that, yeah, that's this one. So, before we get into that, let's talk about the power delivery on this. So VCore VRM is all of this over here. Yeah, it's kind of a mess. So you have this. This is all VCore, and then there's VCore Part 2 over here. And this might not actually. I should have just highlighted that like this. Don't know why I'm trying to be so fancy with it. It kind of looks 3D, eh? Bam. Anyway, yeah. So both of those are VCore. And then over here, we have two-phase memory power for all the GDDR6. And this is on GDDR6, right? I can't remember. I don't really care. It has some... I'm pretty sure it's just regular GDDR6. Funnily enough, from a voltage perspective, I don't think it doesn't really make a difference, because GDDR6X and GDDR6 both run on the same voltage. So... and they both have a 1.8 volt supporting rail, which I have no idea where that is, but it's probably this. I suspect this up here is the PEX rail, so the PCIe interface rail, and then this would probably be the 1.8 volts. But I might be wrong about that. It could be this. Actually, this looks suspiciously like the chip that's used on 1080s. Yeah, GTX 1080s for 1.8 volts GDDR. So it could be that. But anyway, there's a 1.8 volt rail somewhere on the card. There's also a PEX rail, which normally sits at 0.9 volts somewhere on the card. Might be this, might be that. There's also going to be a 5 volt rail somewhere, which could... Unfortunately, those are all interchangeable. For the most part, this could be 5 volts, that could be 5 volts, this could be 5 volts. And one of them's got to be 1.8 volts, one of them's got to be PEX, so... Anyway... But, those are minor rails that don't really matter that much. So that's kind of that. So VCore VRM on this is an 8-phase, and there's nothing funky going on with it because it's just an 8-phase, which is kind of nice for once, because NVIDIA GPUs normally have extremely funky power stage configurations relative to how many phases the VRM relative to how many phases the controller has, because NVIDIA. And I'd really love to know how that works someday. I've never had a chance to actually test how it runs. But anyway, on this card, it's nice and simple. The controller is this chip over here, and that's a UP9512. The 9512 is the 9511's bigger, better brother. It still only goes up to 8 phases, which is what it's, maxed out at here. But unlike the 9511, this thing goes all the way up to 1.2 megahertz switching frequency instead of just 600 kilohertz. So if you feel like it, you can really make your VRM as inefficient as physically possible. And it also has some limited digital control functionality over the I2C interface. However, because this is, however, it's still very analog. So actually, you can still set the switching frequency with a resistor. You can set the load line slope with a resistor. You can set the overcurrent protection with a resistor. You can set the voltage with with a potentiometer and a switch, depending. Like you can have offset voltage mode with a potentiometer and a switch, or you can have locked voltage, like static voltage mode, whatever you want. You can tweak the load line actually with a potentiometer as well if you feel like implementing it that way. So very, very moddable chip. And the data sheet for it is public. So I'll hopefully remember to include the data sheet for this chip down in the description. Because, yeah, that's what one of the things I really like about, well, the thing is this chip isn't unique to this card. There's other things that kind of are. But yeah, the 9512, it's not really the great, like, it's not the best controller you could have, but it's very moddable. And I'm not really planning, like, my plans for this card is basically get it, mod it, bench it, stick it in my daily with all of the mods still attached, and hopefully run it, like, right at the limit of what it's stable at. So, yeah. The 9512 is actually kind of, like, great for that, as in the controller is just super, super moddable. Which is not like what really the only controller you could get where that's not really true is the MPS 2888, and actually the monolithic power systems controllers, which the thing like those are fully digital. So technically you can still mod the PWM vid, but you can't have like a switch for voltage control. You can't have a like that. Well, no, voltage control is fine. You can't do like load line over a resistor. You can't do switching frequency over a resistor. That's all set values in registers on that controller. Whereas with something like this, I mean, if I have the thing is my daily is a test bench. So yeah, if I feel like pushing my daily to the limit, I'm just gonna have like a couple potentiometers probably up in this area. Actually, I could have them up against the rear I/O if I ever decided to put the card in a. No, that's stupid. That's completely stupid. You can't reach behind a system, so no. Yeah, basically just have a bunch of physical, just have a bunch of potentiometers to control the chip. And the reason why I prefer that compared to having digital control is because the software might not work, whereas with like a potentiometer, like either it's there or it isn't. Like there's no, oh, it's being buggy, glitchy, oh, the settings aren't applying, the dongle doesn't detect the controller for some reason. No, it's like if the mod isn't working, the card's probably dead. So, it's kind of like, so I really prefer the hard mod method a lot of the time, because it's just like, there's no wondering about, is this doing the thing? No, it's doing it because it's still running. Anyway, so yeah, that's kind of why I like the 9512 on this. And so that's just set up as an 8-phase here. For the VRM, it's for the actual power stages. We're looking at a bunch of BLN zeros, also known as Alpha and Omega Semiconductor AOZ5311NQIs. That's not a Q. What the hell is that? There, that's a NQI. These are 50 amp DR MOS components. They have a thermal warning system, but that's about it. There's no other monitoring functionality built into them, which makes me wonder, there should be visible current sense. Oh, I guess they were kind of fancy with it. Oh, this is the current sense circuitry, but a lot of the time you'll see like current sense circuitry just between the inductor legs, and to my great surprise, we can't see any of that. I wonder if it's a layer down or something. It's probably a layer down. Or several layers down potentially. Like GPUs tend to have very, very high layer counts, at least compared to motherboards. Anyway, so yeah, 50 amp DR MOS components. On some 3060 Ti's, you might find like 10 power stages instead of just 8, but you won't really find more than an 8-phase controller anyway. So in terms of power handling capacity, what this configuration of power stages means, which I forgot to put the A in that anyway, is that for 1 volt output voltage at 300 kilohertz switching frequency, this VRM is capable of pushing 160 amps while producing about 14 watts of heat. So that's kind of what it's designed for. 3060 Ti's at stock pull, well, this one specifically pulls around 250 watts max. So the 160 is actually sort of towards the peak of the efficiency curve of the power stages, but the card's going to be a little bit above that. Not a ton above that, because of course this just powers the core, and you also have all of the memory, and I think this card has some RGB on it, so which is going to pull like a watt, maybe. But you know, there's the other rails, and those will add up to potentially 30, 40 watts or something. So anyway, so 160, it'll produce about 14 watts. 240 amps, it'll produce about 27 watts. And 320 amps, it'll produce about 47 watts. So this is still fine. 240 amps on the, like, this is still coolable, especially on a GPU where, you know, you have fans blowing directly down onto the card. As long as the VRM comes with decent heat sinks, this shouldn't be a problem to cool. This, on the other hand, is kind of like, yeah, that might actually be a problem. It's not impossible. Like, it's still, you know, within the spec of the power stages, but that's kind of like, yeah, that's as pushing it. And mind you, that's at 300 kilohertz. And as I mentioned before, you can actually very easily adjust the switching frequency on the UP9512. There's just a pin coming off of the chip where you change the resistor value. And that does admittedly reshuffle the I2C address, but I don't plan to use the digital part of the chip at all, so I don't really care. So you can just, and NVIDIA doesn't use it either. That's the other thing, is like NVIDIA GPUs are designed with their entire power, all of the power monitoring and voltage control is designed to work with completely analog controllers, because those are cheaper than the digital ones. So, you know, messing up the I2C address of the device because you're changing the switching frequency just kind of completely irrelevant. But what isn't irrelevant is the decrease in VRM efficiency. So going from 300 kilohertz to 500 kilohertz, things get kind of worse. So from 14 watts, so at 160 amps, from 14 watts you go to 15. So it's not a big deal. That doesn't make a difference. You won't notice. But 27 watts turns into 30, which is kind of like, okay, now we're starting to see some, you know, noticeable heat output increases. This is still very coolable. Like, you know, if I was dailying the card and I've checked that it only pulls around 240 amps, which is going to be way past the power limit, but again, I don't care. And thanks to NVIDIA being hell-bent on, you know, having completely analog all of the controllers on their cards, it's like, well, it does make that very easy to just, you know, modify all of those modify all of the things that get in the way of overclocking. But anyway, and admittedly, like, the 9512 isn't fully analog, it's like semi, but like it's partially digital. But well, the funny thing is the current monitoring is. Like, the current monitoring on the newer NVIDIA cards is really wacky in terms of how it works. But anyway, at 320 amps, on the other hand, things get not great, as it goes from 47 watts to 56. So, like, this was already kind of like, yeah, that might be a problem in terms of VRM thermals. This is not might be a problem. This is a problem. Like, there's a reason why you normally see cards running at 300 kilohertz and not 500. So yeah, but the good news is there's like the reason why you'd want to increase the switching frequency of the VRM is it can lead to better transient response, which means better voltage regulation, which means slightly better overclocking range. Now, there's one other way to do the exact same thing that luckily doesn't change your VRM's power efficiency, or at least doesn't change your VRM's power efficiency anywhere near as much as this does, and that is to just whack on a bunch of capacitors. And that is another consideration I had when looking around for these 3060 Ti's, was just like, so what kind of capacitor modding options do I get with each card? And with this card, there's a lot of options. So for example, we have this right here, right? Like that's a nice, easy spot to get some extra V-core. You admittedly also have this row of unpopulated multi-layer ceramic mounts over here, but the thing is, those are right up against the polymers, and I just like, Yeah, no, we're not fun. This right here is not fun to populate. This is easy. This is nice and far away. Also, the orientation works out like this. So, you know, you could easily whack on like actually probably a bunch of caps. You could well, actually no, these are both ground pads. So yeah, you could totally do this. Bam. So that'll work, you know, whack another one there, whack one here, whack another one here. Might be squeeze a small one there. I probably wouldn't bother with that. Put one over here. This is all really nice and close to the GPU core, so it should hopefully be pretty effective. Unfortunately, this, like, when I saw this cap, I was like, ooh, I wonder if you could, like, and then just run some extra wires, but nope, that's a terrible idea. There's pads over here, so that's not going to work. But there is this right here. This right here is probably, yeah, this should be easy. This area is kind of like I could do this, but that's kind of just fiddly for no good reason. And the thing is, on the back of the card, there's more options. Yes, you have this right here, all of this really. You can fill all of this out. So you could go cap, then you know however many you want. Like actually, you could drag out like a whole line of multi-layer ceramics all the way to here, and then try run a wire or something along to get them. Because the thing is like with capacitor mods, basically, you want the capacitor to be connected as directly to the GPU core as possible. So if you keep stacking them for a very large distance, they just get steadily less and less effective as there's effectively more and more distance between the GPU core and the capacitors trying to, you know, filter the switching noise from the GPU core. But the so that's kind of a down, you know, so that's the downside to just constantly stacking them. But you know, if the priority, like depending on your goals, if your goal is to just add a bunch of extra capacitance and you don't necessarily care about having it be most optimal, then multi-layer ceramics are lower profile than your regular SMD polymers. So you know, just in terms of clearing like a backplate or something, just having a really long snake of multi-layer ceramics works just fine. So that's neat. There's also this right here. You could populate all of this, and unlike on the front, here these are very easily accessible. Obviously, actually you could do this. You could run a snake off of that, and another one over there. Could probably add an extra cap to the side of that. Go like this. Oh, look at that. We've got unpopulated caps. We could run that. This looks like it's probably on vCore. You could probably do something off of that. This looks like it's on vCore, right? Tons and tons of options. Oh, that's unpopulated. We could that would be easy to fill out. You can stack a little cap on top. Well, depending on how much you care about having a backplate, you could add more caps on top of these. You know, depending on how bored you are, you could also mess with the 0603s. Those aren't too hard to do. One thing to watch out for with multi-layer ceramic capacitors, especially on modern GPUs, is they tend to have alternating pads. So, like, it'll be plus, like, well, I'm not sure, I'm not 100% certain on this card, but the reason this is done is it's just done as a method of reducing the inductance between the core and the capacitors. But you'll have something like, you know, positive, negative, and then you'll have positive, negative, and then you'll have positive on this side again. And so you'll have this alternating pattern of where the capacitors connect. And that's just you know, optimization to the power delivery. But the reason why you need to be aware of that is so that you don't like, because if you're really lazy, right, you might be tempted to just like whack a cap like in between two, and if you do that and they're alternating polarity, or well, they're alternating ground and vCore, because the caps don't care. These are multi-layer ceramics; they're not polar. But if the power, like if you have vCore, you know, vCore and ground are alternating, and you whack a cap over both of them, well, you've just shorted out your power plane. So, and depending on the VRM, that can go very dramatically or very undramatically. If the VRM isn't strong enough, it'll just shut down because there's a short circuit. If the VRM is really, really strong, it'll just burn straight through the short circuit. You know, the second of those two options, the problem with burning through the short circuit is it's possibly going to burn something else nearby. So, yeah, that's something worth checking on, especially like on older GPUs. It would be pretty safe to assume that all four of these capacitors are like all of them are vCore on this side and all of them are ground on the other. But with modern cards, that is not a safe assumption to make because yeah, like the thing is, modern GPUs are just produce so much switching noise that you have these like really minor optimizations, like alternating ground and V-core between the capacitors. So yeah, that's something to watch out for. You can't just assume, like, you can't just check this cap and go like, oh, the entire row of them is all going to be the same. It might not be. A lot of the time it is, but it might not be. So anyway, so the 0603s would be pretty easy to stack some extra capacitors on top of. So yeah, nice and easy. Oh, there's also this over here, right? So plenty of options for capacitor mods just all over this PCB. So that's one of the criteria I had for this when you know, looking at these cards. And yeah, this would take a while to fill out, depending on how you know, but depends how bored I am. Anyway, and then actually, since we're already on the topic of adding capacitors, the memory side of things is even better because we have straight up, you know, full-blown SMD polymer pads unoccupied, and also this right here, which, yeah, if you're bored enough, you know, you could fill that out. There's this right here. The one thing I'm kind of annoyed about is there's nothing up here for these memory chips. Like these two, like these memory chips right here, tons of options for extra capacitors. But these two are kind of like, nope, there's just kind of nothing there. So if I was actually working on this card, what I would do is I would absolutely like spend a bunch of time trying to just, you could probably, yeah, you can fit a cap over there, cap here, cap here, cap here, cap there, cap there, cap here, cap there, cap here, here, here. Where else? Those are kind of the easy ones. Depending on how blobby this solder joint turns out, you could whack one over here, I guess. Maybe a little one on this side. So yeah, I would put a lot of time and effort into getting as many capacitors attached in this area, depending on if the memory actually scales with capacitors. Because the thing is, over here, like, that you can whack on these two, and then, you know, I'd still probably put a cap over here, and like I'd put caps on the easy ones, right? Like the ones that aren't super fiddly. Actually, we could do this one on both sides. That's an option. You can also just, you know, stack several of them. Though, if I was stacking them, I would prioritize them over here, just to get them as far away from the rest of the capacitance as possible, because the idea, again, is like each memory chip is going to be producing its own, you know, switching noise as it does memory chip things, and so we want a reservoir of power near to the memory chip, or more like reservoir of energy in the form of extra capacitance near as possible to the memory chips. So yeah, that's actually the main purpose of all these multi-layer ceramics in the first place. So we're just kind of adding more on top of that. And then down here, you just have this one, you know, this optional pad right here. So that one's super easy. The one thing to watch out for with the memory chips is there is a 1.8 volt rail. And there's nothing really wrong with adding extra caps to the 1.8 volt rail. It's just they won't do anything. So it's really like, it's a waste of time. You don't really want to be adding a bunch of caps to the 1.8 volt rail, because that rail is like, it exists, and that's all that really, like it's necessary for the functioning of the memory chips. It is not very significant in terms of actually affecting overclocking. So that rail is just like, yeah, if you end up adding a bunch of capacitors to the 1.8 volt rail, you've just wasted a bunch of capacitors, basically, because they're not going to do anything. But yeah, so, you know, add some extra caps to the memory, add a bunch more to the core. Actually, I'd probably measure it with the oscilloscope, yeah. I just need to find a good measurement spot. I guess you could just reserve one of the larger capacitors from taking measurements from. But anyway, so yeah, that's kind of one of the other considerations I had, which is a really strange consideration, but it's just like, well, I'm like, the thing is, I've run modded cards daily for a while now. Like the RX 580 currently in my daily is modded. I had a Fury X that was, actually I had multiple Fury X's that were heavily modified in my daily system. So yeah, it's just kind of like, I don't think, you know, you might be looking at this, so you're adding all these capacitors, what kind of benefits do you expect? I would be happy if after, I don't know, well, I'd be happy if the memory memory picked up, say, 50 megahertz, maybe. I've had cards where after some extra capacitors, they pick up an absolutely stupid amount of memory clock speed, but I consider that the exception, not the norm. Because there's also a lot of cards where you can add all the caps you want to the memory and it just doesn't do a damn thing. And that's the way it normally should be. If the card picks up a huge amount of frequency because you added a couple capacitors, it's like, whoa, they were really cutting corners on that, weren't they? Um, and then on the core side of things is like maybe 20 megahertz. 20 megahertz from capacitors would be really nice. Because the thing is, it doesn't increase your power consumption. Like, it's not entirely true. Capacitors have leakage current, and then the charging and discharging of the capacitors also counts as power. Like, there's power loss in that process as well. But it has far less impact on your GPU's power efficiency than, say, a 10 millivolt increase in core voltage. So from that perspective, extra caps are basically free clock speed without any, power consumption increase, other than the power consumption increase from the clock speed itself. And that's assuming there was a a voltage regulation issue in the first place that needed fixing. But yeah, so basically, I'm kind of considering this like, oh yeah, there's plenty of convenient locations for extra capacitors. Um, Voltage control, like V-core voltage controller, is super easy to modify. So if I wanted to raise the core voltage by, I don't know, 20, 50 millivolts, maybe as just an offset. The cool thing is, like with the PWM vid circuitry, you can actually just have a switch to disconnect and reconnect the original PWM circuitry, PWM vid circuitry. So you can actually implement your volt mods as like a you can have the option to go between static and actually you can go like volt mod enabled, volt mod off, and static versus offset, which is pretty neat. So you basically get like the full range of voltage control very, very easily, whereas on some controllers it's far more fiddly than that to achieve the same effect. But with PWM vid, yeah, it's super easy. Anyway, let's talk about the memory power delivery, because it's controlled by this chip right over here, and that is a UP1666, and I really like this chip because this thing's been in use since the 10 series, and there's a public data sheet for it, and it also uses a PWM vid interface, and so it's also super easy to volt mod. Now, on this chip, I wouldn't bother with the switching frequency at all, just because it's a memory VRM, and I think like if the switching, the funny thing is, like, so as I mentioned earlier with the V-core thing, where it's like, oh yeah, you could raise the switching frequency, or you can try add extra capacitors, and both of those can lead to better overclocking just because they improve the voltage regulation. Well, with the memory, the same applies. The thing is, it's like I'm lazy, and adding caps is easier than setting up switching frequency control for a 1666. So on the memory, I would only do the caps. I wouldn't bother with the switching frequency mod. On the core, on the other hand, also just because memory doesn't tend to be that difficult to power, so I wouldn't expect it to do anywhere near as much as switching frequency for the core. So, yeah. Anyway, the 1666 is a two-phase controller with built-in drive circuitry. And so that's why on the front of the card, all you see is these two dual NFETs from On Semiconductor, and these are FDPC. We can just read the part number off of them, but that's FDPC 5. Oh no, I do have it in my notes, 5018. And these are dual NFETs, and they're not really good dual NFETs, but it's GDDR. Like, it's what is this? 8 gigs of GDDR6? Yeah, 8 gigs of GDDR6. It doesn't pull that much power. You don't need some crazy high-end dual NFETs for that. And I would actually overvolt the memory. I would probably bump the memory from normally GDDR6 runs on 1.35 volts. I'd be bumping this up to 1.4 for long-term usage. I would be pretty happy running it at 1.4, assuming it scales. Like it's if it doesn't gain any frequency, then running it at 1.4 volts is kind of pointless. But if it does overclock better, then yeah, I'm running it at 1.4 freaking volts. So yeah, and so that's another reason why I'm super happy that this is on a 1666 voltage controller for the memory VRM. However, that's also present on basically all the other 3080s as well. So really, one of the a lot of the most of what I like about this card is just Well, the thing is, there's other considerations to it than just the PCB, but the PCB here is good enough. The VRM's good enough. The voltage controllers are admittedly very common, but, you know, like very easily modifiable ones. Plenty of options for extra capacitors without me having to, like, work too hard for it. Actually, I guess I could probably fit some extra caps over here like that. Also, this might be for memory, so that might be worth checking out. Anyway, so yeah, extra capacitors, memory volt mod, what else is there? Right, current monitoring. So the number one reason why I'm so interested in the FTW3 specifically is this chip right over here, because this is an NCP 45491. It's not a US 5650. And the big difference between these two is that I don't have a datasheet for a US 5650. I do have a datasheet for the NCP 45491. And the reason why this is significant is the NCP 45491 is the chip in charge of monitoring all of the shunts on this card. And, well, with the datasheet, with the datasheet, it's the thing is, so it kind of depends on your card if you need the datasheet for the controller or not. And actually, even if you didn't have the datasheet, there's there's measurements you can take to figure out how it's wired. But it's just like, well, if you have the datasheet, you don't have to check anything. You can just kind of look at the datasheet. Isn't that so much more convenient? Anyway, so what the datasheet solves is this card uses 2 terminals for the shunt resistors. And you can get shunt resistors with with 4 terminals where you'll basically have one small pad, then like a big pad, and then a big pad over here, and then a small pad over here. So the way this works is like these 2 smaller pads go off to the monitoring chip, right? And then the power actually goes through this shunt across from between the 2 big pads. Now, the reason this is done is it can help with getting more accurate voltage measurements. The downside to it, and actually for me it's just beneficial because basically you can, you know, what you can do is you can just remove the shunt, like so, right? You can just bypass the shunt completely, and then you just need to set up some resistors like this. So you put a resistor, and then you put another resistor, and you just go to ground somewhere, screw holes or ground, and bam, you've just faked the voltage reading for that shunt resistor. And now, like, if you do this on every single shunt on the card is literally incapable of power throttling because it can't actually measure how much power it's pulling. Now, the problem with a 2-terminal shunt resistor is you can't do this because there's only 2 terminals. So, for all intents and purposes, that chip is just kind of measuring from the entire 12-volt power plane. Though I guess if I wanted to really bypass it, I could remove the input filtering and here's the really stupid way of working around this, okay? You remove the inductor, you remove the shunt, you go like this, and now you can put your voltage divider on there, which is like, don't do that. This is just dumb. Especially since you really should, you kind of want your input filtering inductor. So that's a really dumb way of working around the shunts only have 2 pads instead of 4. But if you have the documentation for the chip monitoring the actual shunts, well, you can just check the pin out, figure out which pins monitor all of the shunts, and then, set up a voltage divider somewhere nearby. And the voltage divider should be set to... the voltage you want is here. You basically want, let's say we had 12 volts coming in, right? Because this thing is expecting to measure 12 volts on the high voltage side of the shunt, and then it's expecting to measure a couple millivolts lower voltage on the other side of the shunt resistor. So we're going to have 12 volts coming into the divider. And then right here, we would maybe want, what is this? This card uses 5 milliohm shunts, right? Yeah, this is on 5 milliohm shunts. So here we would want, say, 11.995 volts. So the ratio of the resistors gets really whack. So you'd be looking at something like 30. So in the past, what I've used is 33 ohms to 120K. I think, off the top of my head. And that won't give you 11.995 if I'm not mistaken. That'll give you some other value that also works, but... Anyway, so you want something like 11.995, because if you have this set up where it's like 12 volts on this side and 11.995 on this side, and you just feed that to this chip, the chip thinks there's 1 amp flowing through that shunt resistor. And, well, you know, this thing's monitoring how many shunts on this card. We've got a shunt over here, that's 1. On the front, we've got, oops. On the front, we got 2, 3, 4. And I don't think there's a 5th. Yeah, I don't think there's any more. So we've got 4 shunt resistors on this. So if you mod every single one of them, because the thing is, if we go back to the back of the card, right? So we pull, like, the thing is, we can feed this fake voltage measurement right here to all of the inputs of this chip. So we're going to have like 4 wires, or if you, yeah, like you're going to end up with like 8 wires in total going to the chip. So it's not very clean and it's not very compact, but after you do this, the card will be 110% convinced that it is always pulling 48 watts. No matter what is going on, it's going to think it's pulling 48 watts or close to 48 watts, because as the card, you know, load cycles, the actual input voltage will, depending on where you're pulling your 12 volts from for the fake voltage measurement, the voltage will go up and down as the system loads and that kind of thing. So this measurement will go up and down a bit, but it doesn't really matter. The only thing that matters is, like, normally these cards have a power limit of like 250 watts. Well, by doing this, it is physically impossible for the card to ever measure a 250 watt power consumption. Just, it can't. Unless you did this wrong. The funny thing is, you could also set this up to make the card think that it's pulling at like 1,000 watts or whatever. Don't do that. That's dumb. But yeah. So, and this is how I actually have like my 1080 Ti modded. I have a 780 Ti running this way. Admittedly, those were less involved because the chip on those is like 3 inputs instead of 4. I don't know why NVIDIA needs 4 shunt resistors for 3 power connectors. Seriously, like, there's 2 8-pins, there's 1 PCIe slot. How many power monitoring shunts do you need? 4. The NVIDIA answer. And it gets even funnier when you look at 3090s and 3080s, where there's 2 of the damn things. Like, you get 2 NCP 45491s on some cards. And it's like, there's only 3 power inputs. Why do you need 2 4-channel freaking current monitoring chips? Anyway, so yeah, but this chip makes it super easy to just mod well, the thing is, okay, it doesn't make it super easy to, like, it's not super easy, but it makes it much simpler to fake the voltage readings than if you had the US5650. Though, as far as I can tell, though I have a sneaking suspicion that the US5650 is actually pin compatible with the NCP 45491, so on the off chance that, you know, I get an FTW3 and it doesn't have an NCP 45491, well, at least I can compare the PCB I have to the one on Tech Power Up and then figure out if they are actually pin compatible. Because if the components are arranged the same way, then yeah, they're pin compatible. If the components get shuffled around depending on which chip is being used, they aren't pin compatible, and that kind of sucks. But I'm pretty sure they're pin compatible because the US5650 basically exists to do the same thing as the NCP 45491. It follows an NVIDIA specification. You would assume NVIDIA actually was like, yeah, we'd like to have the pinout standardized so we can choose to use onsemi or UPI for supplying our current monitoring chips, which, yeah. Anyway, but like, I'm not 100% certain of that because, again, I don't have a US5650 datasheet, whereas I do have one for the NCP 45491. So that's it. That's basically all I have to say about this PCB. Is just like, it's not the greatest 3060 Ti PCB ever. It's just very, very mod friendly as far as I'm concerned, and mostly because of the 45491. Like, the power plane layout, the capacitor arrangement, like EVGA basically, as far as I can tell, this is basically a reference PCB, and EVGA tacked on this part of it, and most of that part is empty. Actually, it's not. You know what I find really funny about this? I'm pretty sure the pass-through air cooler that these cards, like the FTW3 comes with, would work better if they had just, like, shoved the 8 pins over here. Right? Because you know what's less restrictive to airflow than having holes in your PCB? Not having a PCB. I know. Very complicated. Also, what the hell is this voltage regulator? If that's the 1.8 volt rail, I am going to be um actually kind of disappointed. Like, why would you put your like? This is probably for this. Yeah, this is probably for this chip down here. And even then, it's just like, yeah, you could have just shoved it over here. Oh, one last thing I forgot to mention. The card has input protection fuses, which if you're going to be going to town on this thing with all of the mods and no power limit and all of the voltage, which probably isn't advisable on ambient cooling, but, you know, maybe, like, somehow you figure out how to get an LN2 pot with this guy over here getting in the way. So you're probably not going to get an LN2 pot on the... if you put a CPU pot on it, you might be able to get away with that. As like, it's not going to be attached properly, but, you know. And you'll have to use a riser, which is not great. But, yeah, you know, it's doable. It's not a good idea, but it is doable. Yeah, you're probably going to want to bypass the input protection fuses. I don't know what they're configured for, but you might end up blowing them, and that would suck. There's also an input protection fuse down here. Though, if you're a normie and you're not planning to just, you know, void your warranty, like, completely demolish your warranty. This isn't like slightly voiding it. This is like, yeah, there's no way this is ever getting past RMA after, you know, you do the kind of stuff I described. But yeah, after you just completely destroy your warranty on the card, like, if you're not going to, you know, completely destroy your warranty, those fuses are actually very helpful if anything goes wrong with the power delivery on the card, because they prevent you from causing further damage. Basically, one of the, like, if a VRM fails, they have a tendency to fail high side MOSFET closed. And high side MOSFET closed means 12 volts being just kind of shoved places it shouldn't be getting shoved. And that leads to potentially dead memory chips, dead GPU cores, craters in the PCB, depending on, you know, how bad the short circuit is and how hot it gets. So all kinds of horrible damage. Now, if you have a bunch of input protection fuses like this card has, when your high side MOSFET fails closed, instead of just kind of pulling current until the OCP on your power supply trips, the fuses will blow and it'll stop the card from, well, destroying itself more. And then if you try to power cycle it, well, the fuses are blown, so it won't push power into the short circuit again. Because that's another thing is, like, if you have a card without fuses and it just blows up and then you power cycle it, you're causing more damage. Every time you try to power cycle it, you are potentially causing more and more damage. So the fuses are kind of neat for making the card more repairable in case something does go wrong. Not that anything should go wrong, since EVGA's, like, the power stage is used, like, yeah, it's not the strongest VRM to be ever put on a 3060 Ti, but it's fine. Right, at least within the stock overclocking limits, like, you're not gonna... I can't see a scenario where you'd actually max out the VRM. Well, no, it's not even can't see, it's just like you won't, because you're on the stock limits, right? And then, what else? Where was I going with this? Anyway, you get the idea. So, like, it's not really... Like, the fuses aren't there because they expect the card to fail. It's just like, if something does go wrong, because, you know, things sometimes just go wrong, this makes it a lot easier to repair, potentially makes it a lot easier for EVGA to repair the card, or you to repair the card if you did, like, you know, if you did decide, like, if it's your fault that you broke it. In which case, you might want to leave the fuses on. But it kind of depends on why why the fuse blew, because you might blow them by just pulling too much power without actually harming the card, and then there's the scenario where you blow up the card and the fuses blow with it, blow up too. So, yeah. Anyway, that's kind of it. So I really like the FTW3 PCB, basically because it has an NCP 45491 instead of the US 5650. Other than that, it's not really particularly impressive in any way. Right? We've got what, like, well, I do appreciate that we have some pulse caps over here. Like this cap, as far as I know, is optional, because I've seen some cards without it. And so it's kind of neat that, that one's present, and this one, as far as I know, is also optional. You can see there's a lot of optional capacitors that EVGA didn't bother with, but yeah, so I kind of appreciate that these are populated. Don't appreciate that these aren't. But anyway, so yeah, that's it for this video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both of those help out immensely with running the channel, as in both the Patreon and the Teespring help out immensely with running the channel. And yeah, that's it for the video. So one last thank you to Tech Power Up, and that's it. Thanks for watching, and goodbye. I'm gonna hit the stop button now.